In this video, I will work on the homework that follows the lecture 5.3, focusing on doing calculus with hyperbolic and inverse hyperbolic functions. And in this particular homework, we will focus on doing integration, and it will have two parts: integration of functions or integration involving hyperbolic and integration involving inverse hyperbolic functions. So let's go ahead and start with part one. And here's the first problem. What is the integral of hyperbolic tangent of 3x plus 7? So the first thing we're going to do here is we're going to get rid of the 3x plus 7. We're going to introduce a new variable. It's hard enough to deal with just hyperbolic tangent, and we don't want anything inside to obscure the patterns. So we get rid of that. That means dx is 1/3 of dt. So we can now replace 3x plus 7 with t. And instead of dx, I will write 1/3 dt. So 1/3 comes out. And now the question is, what is the hyperbolic, what's the antiderivative of hyperbolic tangent? And here we may recall that hyperbolic tangent is hyperbolic sine over hyperbolic cosine, and we may do another substitution. So the next substitution will be s, and s will be let's say hyperbolic cosine of t. So what's going to happen next is that we'll find the differential. Derivative of cosine is sine. This is something that hyperbolic functions have slightly different from trigonometric functions. Derivative of cosine is sine. And here you should be able to see the actual pattern. So the pattern is that now we still have 1/3, but my sine dt simply becomes ds. So we have 1 over s ds, and that's an easy one. So we have, that's just ln of absolute value of s plus c, but s is hyperbolic cosine, so we have ln of absolute value of hyperbolic cosine of t, but t is 3x plus 7. And this will be the final answer. So let's go ahead and type it up. So we have 1/3 ln of absolute value of hyperbolic cosine of 3x plus 7 plus c. And the reason why they, for example, don't put the absolute value here, it's because the hyperbolic cosine is always positive. So natural log of a positive number is the same as the natural log of the absolute value of that number. So that's just the properties of absolute values of positive numbers. So in this particular case, we don't have to worry about the absolute value. All right, moving on. We have an integral of x cubed hyperbolic cosine of 5x to the 4 plus 4 dx. And I see the pattern here, so my substitution will be what's inside of the hyperbolic cosine. Why? Because when you take the derivative, you're going to have 20x cubed dx. So dx can be replaced with 1 over 20x cubed dt. And if you look at the integrand, you'll see what's going to happen next. We have x cubed hyperbolic cosine of t, and instead of dx I'll put 1 over 20x cubed, and x cubed is gone. So 120 comes out, and integral of hyperbolic cosine is just hyperbolic sine. But instead of t, we'll have to write the expression in terms of x that t represents. So this is the answer. And this is, of course, hyperbolic sine. All right, so for the next problem, we definitely want to be familiar with some of the common integrals of hyperbolic functions. Which are very similar to in terms of the relations among themselves to trigonometric functions. So it still needs an effort to remember, but not as much effort as one would imagine without knowing those relations. So here, the first step is a linear substitution. So t is 7x plus 12, dt is 7 dx, so dx will just be the 1/7 dt. Now, the integral that we have is very simple. It's just the secant of t, tangent of t, and instead of dx, I'm going to throw 1/7 dt. Now, 1/7 goes outside of the integral, and inside we have secant t times tangent t, all hyperbolic, and that should look familiar. If we go back and check the derivative of what function is secant tangent? Secant. So let's check. The negative secant tangent, right? So that means the antiderivative is going to be negative secant. So the final answer would be negative 1/7 hyperbolic secant of t. But instead of t, I'll have to write what t represents. 7x plus 12. And that's the answer. All right, now we have a very similar problem, but we have cosecant cotangent. So this was number 4. This would be number 4. So we have integral of hyperbolic cosecant of 12x plus 12, hyperbolic cotangent of 12x plus 12 dx. So the substitution here is an obvious one. T is equal to 12x plus 12, so dt is 12 dx, and dx therefore is 1/12 dt. So my integral is the integral of hyperbolic cosecant of t times hyperbolic cotangent of t times 1/12 dt. So we have 1/12 integral of cosecant times cotangent. And if I had to guess, I would say the antiderivative of that is cosecant, hyperbolic cosecant, or negative hyperbolic cosecant. Let's check. So yeah, I guess it's negative. So the answer is, I'll put the negative in the front. So we have hyperbolic cosecant of, that looks weird, hyperbolic cosecant of t plus c. And instead of t, I will write what t stands for, which is 12x plus 12. And we finished the first part of the homework, in which we were focusing on integration involving hyperbolic functions. And now we're going to move on to the integration involving inverse hyperbolic functions. So let's get started. Right away we have an interesting problem, I should say, I guess. So usually the conditions like this just assure that the identity that you are thinking of using is actually the right one. But here we also have to be careful, because some of the integrals of some inverse hyperbolic functions are actually, the answer depends on where the x is. So let's take a look. First step will be to do a linear substitution. So let's go ahead and substitute t with 10x, or the other way, 10x for t. So dt is 10 dx. That means dx is 1/10 dt. So what we have here is now integral of 1/1 minus t squared, and instead of dx I'll write 1/10 dt. And this is something we should be able to recognize. 1/1 minus t squared is the arc cotangent, right? So the pattern here fits perfectly. So if x is greater than 1, then 10x will definitely be greater than 1. So we can use this formula. So the answer will be 1/10 arc cotangent, hyperbolic arc cotangent of the input. But instead of this input, we'll plug in these input. And that should be the answer. I think I'm missing letter C over here. Arc cotangent of 10x. Missing letter H over here. Hopefully that's the only mistake, right? Yep. All right, moving along. All right, so here we have an integral of 1/7x square root of 1 plus 49x squared. And the first thing we're going to do is we're going to make a substitution. So t is equal to 7x, and dt will be 7 dx. and dx will be 1 over 7 dt. Now we plug everything in. So here, instead of 7x in the denominator, I put t. Instead of 49x squared, I put t squared. Instead of dx, I put 1/7 dt, but I'll write 1/7 in the front. And now this should be in your table of integrals, and you should at least recognize that this is some sort of pattern, and we need to, and we can take advantage of it. Now, let me also pull up this okay, so the difference is this is minus, this is plus. Now, your concern should be here about the actual formula has absolute value of x, right? We don't have absolute value of x, we have just t. So if you assume for a second that this is positive, then everything that we're about to write will be true. So I think it's a mistake not to mention that x should be positive here, but most students don't care anyway. So here's the answer. It's going to be, I already forgot, arc cosecant, negative arc cosecant, right? So we have negative arc cosecant hyperbolic of t, and rewriting it once again. This time instead of t, I'll put 7x, and that should be the answer. Now, one way to check is to just differentiate this function, and you will see exactly how things work out if you differentiate this function using the chain rule. So I guess let's check the work now. So let's make sure we did the right derivative. We have x interesting. One way to check will be to, let's see, we only have one attempt left. So I'm going to define a function which is my answer. So negative 1 over 7 arc cosecant, hyperbolic arc cosecant of 7x, right? So this is my function. And I'm going to graph this function, which is the integrand. And we see that this is what it looks like. And the goal is to check whether the green function is the derivative of the blue function. So I'm going to also graph the derivative of the f function. And looks like if we restrict the domain, so as you can tell, it's not true everywhere, but if we restrict the domain to positive values of x, then it is true. So did I make a typo? Hyperbolic arc cosecant of 7x plus 7. Yeah, I don't know what it doesn't like about this answer. Interesting. So I'm gonna press the last thing I can do is bring the big guns here and actually, because I'm really concerned now with whether I'm being graded fairly here. So let's see. Oh wow, it wants us to enter cotangent inverse. What's the derivative of cotangent inverse? I feel like this is due to some sort of identity here, because 7x and 1 plus 49x squared have like some sort of relation there. But that actually brings a good point. So cotangent inverse of square root of that, is that the same thing? So let's see. Negative 1 over 7 arc cotangent of square root of, what was it, 1 plus 49x squared. And what do we see? The black graph. The black graph is same as blue graph, right? So yeah, interesting. I think it's a glitch. So let me try to submit again. So we're gonna take a loss on this one. Let's see. That's interesting. Is that true? If this is true, then this is interesting. Cosecant inverse of absolute value. So basically they're saying to throw the absolute value in the answer. So if I throw the absolute value in here, that's an interesting relation. I feel like it's interesting. So this is like an alternative way to actually write the formula without restricting your domain in any way. So the correct answer here would be to put the absolute value instead of adding this additional constraint. Just put the absolute value, actually does the trick, which is pretty cool. All right, so we took a loss on this one, so we need to buckle up and continue working. So we have, this was number 6. Let's do number 7. Probably very similar problem. We have integral of 1 over 13x square root of 1 plus 169x squared dx. So the substitution t equals 13x will do the trick. So dt is 13 dx. dx is 1 over 13 dt. And now we have 1 over 13 integral of 1 over t square root of 1 plus t squared dt. And I'm curious, is it the same one? It's actually pretty much the same thing, right? So this time we're not going to make the same mistake. So the answer is negative 1 over 13 arc cosecant of absolute value of 13x plus c would be the right answer. Let's see if it likes it. Yeah. All right. Looks very similar but different pattern. So the substitution here is actually 6x, so dt is 6 dx, dx is 1/6 of dt, so we have 1/6, so this is going to be dt, and now we have 1 over t square root of 1 minus t squared, and this is also a known pattern here, so we have, this is arc secant. And here we don't have to worry about the absolute value. So the final answer is this. Oh, great. Is the let's play with it same way, but so this is the answer. This is our function. So this is our function. The purple where is the purple though? So that's the purple. That's the integrand. Oh, so we also have something going on this negative side. Why? So the domain of the arcsecant, the range of arcsecant function is just this. Well, the domain is from 0 to this number right here. If it's another absolute value, that's going to be really interesting. If we put the absolute value here, what's going to happen? It seems like for some reason this, again, let's put the absolute value here. it's really weird that it insists on this absolute value. Anyway, just be aware of this. All right, next problem. Same first step, we do substitution. T is equal to 12x, so dt is 12 dx, so dx is 1 over 12 dt. Now we go in and plug everything in, so we have 1 over t squared minus 1, and instead of the x we put 112 dt, and we write 112 on the outside. Now this should be some pattern. The integral of 1 over square root of t squared minus 1, that looks like hyperbolic inverse arc cosine. So the answer is arc cos of t. And instead of t we put 12x. And if it doesn't like it, and it's going to be about this absolute value again, I'm going to be really mad. Arc cos 12x plus c. Missing a c. Next problem. The substitution is 11x. So 1 over 1 minus t squared, that's some pattern again. Which one? It looks like arc cotangent. So this should be the answer. And it looks like we finished this homework. So if you have any questions about integration involving inverse hyperbolic or hyperbolic functions, please let me know.